Hi, my name is Fomitchev-Zamilov, and I would like to tell you more about the pre-dynastic Egyptian ancient vase analysis that I performed recently using Beall's vase collection and the CAT scans of the vases therein. Matt was very gracious to share with me CAT scans of his collection, and he undertook a major feat. He scanned no less than 22 or maybe now more objects from his collections that look kind of like this. And what he has done that's particularly useful for scientific analysis, he used CAT scans of his vases. So CAT device is an X-ray device, so it can see through the vase. And the greatest advantage of CAT scan versus optical scan is that we get to see inside the vase. So with optical scanner, we can see the outer surface really well, but the inner surface hardly at all. But with CAT scan, we can see both inner and outer surfaces. And I'm particularly grateful to Beall that he has chosen rather expensive and rather high accuracy and high precision, high resolution CAT scanning process to acquire three-dimensional images of his collection. So here we see a CAT scan image of this particular vase from Beall's collection. Yeah, he calls it Beall. So this is an STL file, and it's a very high resolution 3D model of the vase. And we can see both inner and outer surfaces in vivid detail. So to analyze the vase, I had loaded the STL files that were, the 3D image scans of objects in Beall's collection in MATLAB. So I had to write code in MATLAB to automatically process each scan. And the way this code worked, it loaded the STL file and then it sliced it into horizontal slices. And each slice kind of looks like this. So on this chart you see a bunch of slices. In fact, I took 100 slices through the model, which were along the Z-axis. And you see each slice is more or less a circle. If the vase is perfect, the circles are perfect. If the vase is handmade, the circles are not so perfect, maybe a little more elliptical or skewed. But the way analysis goes, each slice is analyzed for how circular it is. So there is a root mean square error calculated for each slice to tell us how much it deviates from perfect circularity. And also, we get a center of each circle. So once we sliced the vase into 100 slices, we can see whether the centers of each slice align, and that's a measure of circularity. And on this plot you see each point, or rather 2 points in this case. So as the slice goes through the vase, we get points for the inner surface, which are colored in orange, and we get points for the outer surface, which are colored in blue. And this tells us which points we're using for our calculation to evaluate the quality of an artifact. And on this chart, we can see the root mean square errors from circularity. So the blue plots are for the outer surface and orange plots are for the inner surface. The horizontal axis is in thousandths of an inch. So we can see that the deviation from perfect circularity of the outer surface of this vase is on the order of 2 thousandths of an inch. And for the inner surface, the hollowed out core here is about 3.5 thousandths of an inch. This other plot tells us the scatter, so the centers of the points of the circle for the inner and outer surfaces. How do they scatter? And we see that the scatter here is pretty uniform for both inner and outer circles. And the difference between them is just about maybe 1/1000th or 2/1000ths of an inch. So what it tells us that this vase was hollowed out with such a precision that the center of the inner surface is aligned with the center of the outer surface, within basically 1/1000th or maybe 2/1000ths of an inch. Each 3D scan of a vessel like this is an STL file that's anything between quarter of a gigabyte to half a gigabyte in size. So there are lots of points and opportunities for many high-resolution slices through the model. Because of this vast amount of data, the MATLAB code that I've written takes about day and a half, sometimes 2 days, sometimes even longer to crunch through all the numbers. So to put things in perspective, when we use a ruler, it's one measurement. So in this case, we're taking hundreds, if not thousands, of measurements, which are slices through the model to evaluate how perfectly the slices fit a circle. So that's a lot of number crunching that takes several days to complete. And at the end of the day, I get a quality metric that I plot in my Excel spreadsheet, and that spreadsheet allows me to see where a particular artifact I analyze, where does it fall on the scale of quality factors. And this is the same chart I used in my blog, and the same chart that Matt Beall has illustrated in his Limitless podcast. And out here we see the precise artifacts are colored in green and imprecise are colored in blue, and red are being the two handmade vases made by Olga Vdovina, and the orange bars correspond to the modern day artifacts that I purchased off eBay to compare against modern technology. And we can see that the precise vessels from Matt's collection are better, the same or better in quality, in machining quality or in fashioning quality as the lathe-made artifacts that were made in present day, whereas the handmade vases made by Olga Vdovina are far worse in terms of quality compared to these precise artifacts, and they are on par with the rest object in the Matt Beall's collection. And it's interesting to see that when you eyeball both precise, which is this beehive, and imprecise, which is this vase object, to a naked eye, they look very well made. The surface is nicely polished. The object is reasonably symmetric and reasonably round. It's very hard to tell whether or not it's precise or not, but this kind of mathematical analysis in MATLAB, without any question, without any doubt, is able to tell that this is perfectly circular, perfectly symmetric. The inner surface is exactly aligned with the outer surface, whereas this is clearly handmade. It only appears to be well made because naked eye is not able to distinguish minute deviations from perfectness, but the machines, the X-rays clearly see it. So this artifact is 20 to 30 times worse quality in terms of the quality metric as defined in my analysis compared to this artifact, and that's what this computer-based analysis in MATLAB clearly shows. So I was astonished to see that Matt Beall has in his collection 11 artifacts that I classified as precise, and this is one of them. And precise meaning the quality of fashioning of this object, which we think is a pretty nasty ancient Egyptian stone vase, probably made out of basalt. So the quality of fashioning of this object is on par, and is actually better as the same modern object or similar modern object that was made on a lathe. So this is a gift shop type stone vessel that's been clearly machined on a lathe, and you can see it, and you can buy a number of these. So the computer analysis tells us that these two artifacts are made using a very similar technology. So we don't really know how ancients made their stone vessels, but what my analysis reveals that they were not made by hand. It's inconsistent with manual labor. It's consistent with some kind of machining. Granted, I don't know what machining it is, but it's consistent with modern machining. So one of the conclusions of my analysis, and if I didn't know that this beehive type stone vessel was of ancient Egyptian origin, I would have said, well, it probably was made in modern time. And that's why I think my analysis is useful, because it's able to determine how a particular object was made, whether it was made by hand or whether it was made using a machine or a tool, and the analysis can clearly tell that. And that's why I think it could be useful for classifying archaeological artifacts belonging to different cultures or different periods, because as manufacturing or fashioning quality improved, so is the quality of artifacts. So if you obtain a 3D scan and crunch it through the code, the quality value that you get will be helpful in attributing or in dating the artifacts. Again, my name is Max Fomitchev, and you can read more at my website maximus.energy. Thank you.